So let's do this. Welcome to ThatITShow. Today we are going to be different. Yasmin here. We are going to be talking about 602 processor. And since Wedren is away, I'm going to do first of what is going to be a couple of different episodes in which I'm going to cover 602, its history, the idea behind the processor, and why do we think that this is going to be the processor that will not die. Let's roll the intro. Okay, so the year is 2024, and we are still talking about the processor that has been on the market for the last 50 or so odd years. And this is one of those things where we need to take a look back, try to understand what we are talking about and why we are talking about this, and try to understand actually when to start when we are dealing with hardware. So this is one of the incarnations of the processor that we are going to be talking about. It's called the MOS 6502. It's been a design that has been changed over the years, but its initial version still remains one of the most influential processors that there are on the market. And it usually came in this package, or when you take a look at how the die looks like, it looked a little bit different, something like this. This is one of the first processors that was available on the market when it came to mini computers, or you could say that this was one of the processors that redefined how we understand what the computers are. First and foremost, because it was one of the first processors that was available to the open public, and it was affordable when it comes to the normal, regular guys who could create their own computers. So when this processor came out, it was designed to be as simple as possible, as cheap as possible, and one of the ideas behind it was to enable everybody to learn how to program it and to create different computers based on it. This was way back then when having a computer meant that you had to design the entire system, create the entire software for it, and then more or less hope that the market is going to accept you and use your computer. And this was probably one of the most dynamic days when it comes to computing, because almost everybody could create their own computer and could write for that computer and could create programs. So this was more or less the popularization and the a result of hard work of many people that resulted in the computers being available to the masses, as we could say. Why are we even interested in this computer? It's extremely old. It came out in 1975. This means that it is going to be hitting 50 next year. And based on this, we could say that after 50 years, maybe it's time to put it to rest. But the reason why people are still interested in it is not the value that came from this being an old processor, but nostalgia is part of it, but this is not the entire story. The entire story is basically that this is one of those things that enable you to learn a huge amount of things and huge amount of different topics because it was there when those topics were created. So some of the names of the different parts of the processor, some of the names of the register, for example, some of the names for the interrupts and so on, which I'll be covering later, defined how we use this naming conventions still today. So this was one of those things when you had such an influential piece of hardware that it made sense to use it back then, but it also makes sense to use it in education even today. Let's just go through the general specs. The initial processor was designed for the 5-volt input. It's also had so basically it was using the logic that was defining the 0 as being between 0 and 0.8 volts. The 1 was between 2 and 5 volts. It was exclusively 8-bit inside, but it used 16-bit address bus, which meant that it was able to use 65,536 values, or 64K of memory, or it was able to address that much memory. This covered the entire memory, including the communication with different hardware devices and outside devices. And this is where we need to learn a few things before we start coding and we start talking about the processor. The processor itself, as I said, is extremely simple. It consists of a couple of registers. By a couple, I mean actually 5 of them, 6 if you count the program counter. And program counter is the only one that has 16 bits. The rest of them are 8-bit registers, and they are used to store different data points or different types of data inside the processor, both to enable it to work and to enable it to communicate with the software that is running on it. The thing that we must stress is what the registers actually are. When it comes to memory and when it comes to today's processors, we are rarely talking about registers, but registers are extremely important when it comes to older processors, but when it comes to processors as such, even today. Memory, as we know it, is usually the memory that is outside of the processor. Registers are directly inside, and the registers are part of the processor that are intended to enable calculations and enable operations that the processor is able to do. So when we are dealing with data that the processor needs to compute on or work on, this data needs to be in the registers. So what we are going to do is usually we are going to either get some information from or data from the memory, or we are going to get some data from the registers to the memory. And this is the main way in which we are going to deal with our programs and with the data that we are going to work on. 6202 has more or less 3 registers that are intended for the user, and 3 that are intended to enable the processor to function. On this slide I have all of them. A, X, and Y are the registers that are intended to be general purpose. By general purpose I mean that they can be used all over the software, and they are intended to hold 8-bit data, and you can do some operations on that data depending on the instruction that you are going to use. Only difference between those processors is in the way that they are wired inside the processor. So the registers, it's or to be more precise, the thing about these registers is that they are differently wired inside the CPU, and this means that some operations are possible on some of the registers and some are not. We are going to go into details when we mention different operations, but in general, register A is the one that enables you to do the most operations, and X and Y are there to be more of a support, or more of a different register to hold different parts of data that is going to support the main operations that you're going to perform on the data in the register A. P, S, and PC are registers that are rarely used directly, or to be more precise, they are designed for the special use of the processor itself. And I'm going to go into details of what they mean. But generally speaking, program counter always holds the information about the next instruction that is going to be performed. S, or stack pointer, is the processor register that is going to point to the top of the stack, and the P register is going to be the flag register that is going to hold the different flags that mean different things when it comes to what happened or what is currently going on in the processor. 6502 is extremely simple, and this is reflected in the way the P register works, or the flag register works. Some of the bits that are there are not used. There is only one bit, basically. The 7 of them are used, one is not, and it is always 1. The idea being that you need to know, if you need to know what is happening inside the CPU, you can take a look at the different bits in the P register and see what is happening inside the processor, what is the result of the last operation, and what happened. For example, there is an overflow bit that means that has a meaning of telling you if the overflow occurred, or to be more precise, if the operation that was the last performed went outside of the span for the 7-bit numbers. There is a bit called negative that provides you with the information: is the number currently in the accumulator positive or negative? And this usually is used when we need to test for a number being negative after an operation that we performed. There is a bit called B, or break, and this means that the break command was executed, and we usually use it to be able to recognize if the interrupt was hardware or software based. If the interrupt was done by the software, we're going to see a B here, so B is going to be set. If the interrupt was hardware based, so it was initiated by the outside hardware, the B is not going to be set. We are going to be talking about a little bit about this later when we go and deal with the assembly language. Also, there is a register that you won't see, or the register bit that you won't see anymore on the mother processor, that switches the mode. Usually the processor uses a binary code binary code decimal notation, but you can also switch it to decimal mode. There is a switch or a flag that is able to disable the interrupts. There is a flag that is set if the last of the operation resulted in a 0 being written to the accumulator. And we have a carry that is used to see if the last operation had a carry set, or to be more precise, if the result of the last operation needs more than 8 bits to store the result. So this behaves as a 9th bit that can be set while using the CPU. Stack pointer is interesting because this is one of those early things that were defining how to use and how to store the data inside the memory or inside the processor. The data needs to be stored, And when you are dealing with a software operation, any software operation, you're usually dealing with multiple points of data or multiple data values. 6502 is extremely simple, and there is no way to store variables. You cannot say, okay, the variable A equals something or variable B equals something. What you can do, you can refer to locations and you can store the data there. If you are able to structure your data in such a way that you know how this data is going to be sorted, then you can use something called a stack. A stack is part of the memory. In this particular case, hardware coded as locations between 101FF hexadecimal. So something called the first page of the memory. It is 256 bytes of memory, and the stack pointer is a value that is going to show you where the stack is right now. What does it mean to point to the stack or where the stack is? When the computer starts, or when the CPU starts, because we are dealing with the CPU now, the computer itself is the CPU, the stack pointer is going to be reset to the top of the range. So it's going to point to 1FF. If you do any kind of push instruction, it is going to decrease the stack pointer. So the stack pointer is going to be decreased by 1, and it is going to move to, for example, from 1FF to 1FE and so on. Stack pointer is 8-bit, and you can see that the location is 16-bit. This is because the offset is always 100 hexadecimal. So we are always dealing with the values between 100 and 1FF. So the stack pointer is going to just show FF in this example, and 1 is just going to be a thing that we are going to presume is the offset. Offset, the stack pointer itself is last in first out type. So the last information that we put on the stack is going to be the first information that we can get. And also there is no control over the stack itself. So what we can do wrong is that we can break the stack or do a stack overflow, meaning that we can cycle the stack, and once we reach the bottom of the stack, we are going to automatically go back to the top, and this is going to break the things because we can only store 256 bytes of information. If you try to store 1 byte more, we are going to overwrite the first location that we stored. And the other thing is that we can directly influence the stack. So this is one of those things where 6502 is simple, but you have to pay a lot of attention in order to be able to successfully create your own programs. Some of the emulators out there are aware of the way the stack can be broken or the stack can be overflowed. So some of them are going to warn you that the stack has been overflowed, and they're going to throw an error. But this is not the something that you can depend on. So if you are writing for the actual processor, or you're writing from a different emulator, check if the stack pointer cycles over. So if it goes below below 00, and if you decrease it by 1, it's going to become 1FF or go back to the top. This means a stack overflow. And if you see that your compiler or your emulator is not warning you about this, have in mind that it can be like that. So the stack is not going to be monitored by the processor itself in its original state. The last register that we are going to deal with today is called program counter. Program counter is 16-bit, and this is the only 16-bit register, and it is there to store the location in the memory where the last instruction, the next instruction that you're going to run is stored. So when the CPU needs to execute the next instruction, it is going to read the program counter fetch the instruction from the memory, and then execute it. The instructions on the 6502 are always 1 byte opcode, so operation code, or what the instruction does, is 1 byte, and then we can have 0, 1, or 2 operands, or parts of data that this instruction is going to operate on. It is also all dependent on the instruction that is performed, and if you need to know what is the length of the particular instruction, so how many bytes does it take in the memory, you can either look it up or in the manual, or you can simply calculate it, because as soon as you start working on 6502, you're going to understand that these things are pretty basic. Instructions that are not influenced by data, like increase or decrease, are usually 1 byte instructions, and then instructions that require operands are going to be the longer instructions, and all the manuals are going to provide you with the exact value of for different versions of the operation, so you're going to be able to see how long the instruction actually is. Instructions themselves are or can be written in 2 ways. You can either write them out as mnemonics, so usually 3-letter abbreviations of the command, or you can directly write down the opcode and use it directly in hexadecimal mode. It can be done, and people that have huge amounts of experience with 6502 usually do it this way because it's much quicker. But on the other hand, it's much easier to understand, to remember the mnemonic, and this is the idea of the mnemonic being something you can actually memorize. Instructions can use direct and indirect addressing, and we are going to deal with this later when I'm going to be talking about the different examples. For example, one of those instructions can be something called LDA, so load accumulator or load A with value. The value is going to be inside the memory. Depending on the way how we call this instruction, you're going to either refer to a location in the memory, or you're going to be referring to an actual value that you're going to put in the memory. Then there is an instruction called ADC that is intended to add. So it is going to take whatever is in the accumulator, it is going to use the operand of the instruction itself, and then add those 2 values, and use the carry to reflect if there was overflow, or if there was anything that if there was a bit that wasn't able to be put inside the A register, or if the result, basically the result was 9 bits long. SBC is subtract with using carry, so the opposite of add, and you can, for example, set carry and clear carry directly. And the reason why I chose these 5 instructions as examples is more or less because they can, depending on how they are called, they can be from 1 byte to 4 bytes long inside the memory. And this is one of those things where a single mnemonic, for the example LDA, is going to end up being different opcodes depending on what the actual command or instruction needs to do. This is probably the right place that we just quickly detour from the thing that we are talking about and just mention one thing. CPU does not understand what an instruction is. It understands opcodes, and basically one instruction that we think about as an instruction, for example LDA, is going to map to different opcodes depending on which values are we using as operands. So for example, if we are using direct values, this is going to be 1 opcode. So the processor is going to take whatever we noted down as the value, and it's just going to put it straight into the accumulator. When it comes, if we use the reference to a part of the memory, the processor is going to first go to the memory, load the value, and then put that value into the register A, and so on. This is going to be different opcodes, because different opcodes means to processor that he needs to do, or it needs to do, different things. When you first see the hexadecimal notation of the instructions compiled, so or assembled, you are going to see that one command can result in different opcodes. This is normal. This is exactly the thing that I'm talking about. Depending on how you use the operands and which version of the command instruction you are using you are assembling, opcodes is going to be different, and this is something that you are going to quickly learn to understand, and it is going to take you probably a couple of hours before you are able to actually read hexadecimal code inside the 602. Numbers are differently represented when it comes to assembly, because the assembly itself needs to be able to understand what you are dealing with. So if you just note the number in the assembly, you are going to, by assembly I'm meaning assembly language, you are going to be referring to the decimal value of the number. So for example, in this example, the 24 means 24 decimal. If we put the $sign before the value, we are referring to the hexadecimal value of the number. So this is actually 36 decimal. If we put the hash before the value, this means the exact value of 24. In this particular case, we are meaning hash 24 means a decimal number 24. And if we do both things, so the hash and the $value, this means decimal 36 or 24 hexadecimal. This is going to be important later, because if we omit the hash, this means that we are referencing a location in the memory. So we can be using directly addressed parts of the memory, and we are going to be dealing with memory differently, because we are going to be using something that can be considered pointers if you are into C. Since 6502 more or less does not understand anything other than either a part of the memory or the direct number being referenced. When it comes to instruction set, and if you are in any way acquainted with how, for example, Pentium or Intel processors of newer generations work, you're going to be probably surprised that this is everything that the instruction set is able to do. It has 4 addressing modes. We are going to be dealing with something called immediate, absolute, absolute indexed, and indirect indexed mode. And instruction categories are just a way of trying to explain how the instructions are grouped. They're going to be either dealing with the memory, the register transfer, they're going to be dealing with the stack, they're going to be dealing with the arithmetic, logical operations, branching, calling and returning from functions, dealing with flags, dealing with interrupts, and doing a no operation, or just more or less waiting for the next operation to occur. It probably, if you haven't done any assembly language programming, it doesn't make sense to you to do a no operation. But sometimes you need to wait for something to happen, so you need to skip a cycle, and you need to make your processor wait for the entire cycle, because you're simply waiting for something. Now for the addressing. There are 4 different types of addressing in the 6002 world. The immediate one is when you are dealing with directly with the memory. And this, or directly with the values. For example, if you say LDA hash $04, you are saying put the value of 04 hexadecimal inside the memory, and the memory itself is the accumulator or the A register. Then in this example we are doing clear carry, and then we are adding the value of 3 to the A, then we are adding the value of 2 to the A, and we are adding the value of 1 to the A being the A register and the value being the actual number that is on the screen. This means that we are not dealing with the addresses, we are addressing the CPU. So sometimes people, when they see the word addressing, mean we are addressing the memory. No, we are not talking about addresses, we are addressing. So we are talking to the processor and we are giving it immediate values. The immediate values being 4, 3, 2, and 1 in this particular case. Absolute addressing is different. What the actual absolute addressing means is that we are dealing with the value of the memory location that we are going to be using to do something. In this example, we are going to be simply filling part of the memory, exactly 4 bytes of the memory, with different values. When we start with the first command, LDA4 hash $04, this means put the hexadecimal number 4 into the register A. STA means store from accumulator or store from A, and this is going to be getting the information from the accumulator to the location that we point to. We are pointing to the location hexadecimal 0203, and you can see here that we are using 16-bit number or 2 bytes for a number, because the program counter and the memory itself, the addressing space of the memory, is 64K, so we can use 2 bytes to directly talk to the memory. So what this first part of the example does is it uses the accumulator to fill the values from 200 to 203, so the 4 bytes starting at 0200 to 0203, and it's filling it with values of 1, 2, 3, and 4 hexadecimal, location by location. The reason why we are doing it backwards is because this is the usual thing that you do when you're dealing with the assembly. Usually the normal way of doing things is going to be from the highest value of the memory to the lowest value in the memory, simply because it usually makes things easier when it needs to do the addressing and the other things. If you want to now add those 4 bytes that we stored, so we put 1, 2, 3, and 4 inside those 4 bytes in the memory, we can now directly talk to them by using the memory locations. So now we are omitting the hashtag, and this means that first you're going to load whatever is in the location 0203 into the accumulator, clearing the carry, and then doing the addition and just adding whatever is in the location 202, 201, and 200. This is what you would do if you used what would be called pointers. So you are referring to part of the memory, getting the information out of it. The information itself is 1 byte long, so you are putting 1 byte into the accumulator, and then you are adding a value to it. And in the end of this, you're going to end up with result inside the accumulator, and the carry is going to be set if the result is bigger than 8 bits. There is also something called absolute indexed addressing, and this is the reason why sometimes we are calling the X and Y registers indexing registers. The programming itself usually requires you to do a lot of iterations, and it requires you to deal with a lot of data. This is going to be sequentially stored. Since 602 only has one accumulator, and it can only store a single value, or you can use the stack to store multiple values, but you also need to iterate through them. There is a way to do the indexing. In this particular case, what we are doing is we are loading the X register, the indexing register, with the value of 3, and then we are referencing the location that is going to be referenced as $0200, X. This means in assembly that we are going to be referencing the location that is going to be the value of 0200 plus the value of X. So we're using the X as the index. In this particular thing, what we are doing is the index is 3. So we are referencing the value in the location 2003. Then we are loading that value into the accumulator. Then we are decreasing the X. This is the dex command. It doesn't have any other operands. Then we are doing the same thing with the next location. So in this particular case, this is going to be 2. So 202. Then we are decreasing the X. 200. We are adding to the information from the location 201, decreasing the X, and then adding from location 200. Functionally, this is going to be the same as the previous example, but we are doing the addressing by using indexes, and this is something that we are going to be doing a lot, since this is going to help us do a lot of things in much quicker way than it would be to simply just write out the different addresses. And the other thing is that sometimes we don't know how many passes or how many locations in the memory we need. So by using the indexes, we can just create the value that we need, and we can store as many values as we need to, and just skip over the rest of the memory. Now, when I'm dealing with assembly, I usually do this example, and I show it to my students, since this is the way how to do a loop. Why a loop's important? Because this is the first time that we are going to be dealing with how to make a decision inside your assembly. Assembly by itself is a strange beast. It is trying to, and it is always going to try to execute one instruction after the other. So the assembly itself is not going to jump in the memory. What needs to happen is that you need to make jumps, or usually they're called conditional branching, or branches. And you need to tell the processor where to go if a certain condition is met. What we are going to do here is we are going to go step by step and explain what each command is. And I do recommend you go and take a look at those commands and try to use this in the emulator that we are going to be dealing with later. So LDX hash $03. Store the value of 3 hexadecimal into the register X. Then go to the location 200 plus X, so in this particular case 203, and get the value from this byte in memory and put it into the register A. Decrease the X, so X is now going to be 2. Clear the carry, and then the next bolded command is something called the label. It's not an instruction. It's just a way of telling the assembly where the start of the loop is. So the assembly itself is not going to be able to understand where to jump unless you tell it where to jump. So this is more or less of a marker. it just tells the assembly this is the point where you need to jump when you're jumping, and you are changing the way your instruction sequence is going to work. Next after this, we do the addition with carry. We are adding the value from the location 200 plus x, so 202, decreasing the x, and then comes the important instruction. BPL means that we are going to be branching when the value is positive. This means that your command is going to be going back to the add loop location, so the label that you have put inside your program, if the result of the previous command was positive. Since we are decreasing the register X, this is the last command that has been executed. So until we hit 0 and try to decrease it by 1, so this becomes a 0, becomes a negative number. This loop is going to loop itself. So it is going to go through the iterations for the values of 2, 1, 0, and then it's going to break out. By breaking out, I mean it is just going to go outside of the application, and it is going to try to run forever, depending on the emulator that we are using, and we are going to be using 2 of those. Your emulation is either going to stop, or you are going to have to stop the emulation yourself, because it doesn't know when to stop. The last thing that I failed to mention, and that I need to mention, is something called indirect indexed addressing. Indirect indexed addressing is a thing that is required when you are dealing with matrices, and when you are trying to create additional ways of referencing parts of the memory. And the idea is that you can read the value from the memory, and then you can use an index to use this value and create a pointer or a location, pointer to the location in memory where the information is stored. Let's use the example, because this one is much more based on examples, and it's easier to understand when you have an example before you. So the first 4 commands are simple. We are storing the values of 00 and 02 into the locations 10 and 11. By using just 1 byte or 8 bits for the location, we are referring to the location 0010 or 0011. So we are referring to the very start of the memory. Then we are going to use the register Y. Register Y is usually used when you're dealing with indirect indexed addressing. And we are going to put the value of 3 into it. Then we are going to do the command that is that has the value of $10 in parentheses, then a comma, then a Y. What does this mean? This means for the processor to go to the location 10, to get the value from there. Once it gets this value, to add the value of Y register to it, then to go to this value, to use this value as the reference in the memory, go there and then grab the information that is inside the memory stored on this location. The thing is that when you do it like this, what you're going to be dealing with is not only the thing that you are going to be dealing with the location 10, but since we are referencing memory, what the processor is going to do, it is going to load the location 10 and 11, because the memory is always referenced as a 16-bit number. So it is going to be using both the values in the value 10 and in the location 10 and location 11. It is going to add the Y to it, so it is going to become location 11 is 02, location 10 is 00, so it's going to become 0200 plus the value of 3, and then it is going to do a loop, and it is going to just do the same thing as it did the last time. When I am dealing with this, I also need to mention one thing. When you are using the indirect indexed addressing, it is a strange thing. The strangest thing is that you are always going to be referring to the first location in the memory, and this location is going to be the one that is going to be read, and then the instruction that is using this kind of addressing is also going to read the location after the location that you gave it, because it needs the 16-bit number. The values that are going to be stored in the memory need to be stored as little endian numbers. Endianness, or the value, the way the value is stored in the modern processors, is can be either little or big endian. Please don't use the any other terms. We are talking about little end first, so the part of the number that is stored in the memory is a little part of the number, so the least significant bit of the number. Or big endian means that the first byte that you're reading is the most significant bit. For example, in our example, we are dealing with locations 10 and 11, and we are storing 00 in the location 10, and we are storing 02 to location 11. When we decode this as little endian number, it actually means location 200, because the little end, or the least significant number, is the first, so 00, and the most significant part of the number is the second, so 02. So 0200 is the actual value that we are going to refer to. A register X cannot be used here. Just as a side note, the reason why we have this strict ways of using different commands is because the processor itself is structured like this. Why we cannot use location the index register X? Because the processor itself is going to use it to store the information where it needs to go. Register Y is directly wired to be able to be used in this mode. So this is just a thing on how the processor works, and we need to make sure that we are not stepping on the toes of the processor while it's doing its thing. There are also some other things that you can do. There is something called zero-page addressing, and this is when you reference the values in the memory as single byte or 8-bit numbers. And the reason why it's called zero-page is because the memory itself is structured in such a way that we are referring to each block of the memory that is 256 bytes long as a page. So when you're dealing with pages like this, your zero page, or the first page when it comes to the way humans count, is going to be the first part of the memory. And then once you get over the value of 100, you're going to be dealing with the first page. Then the page after this is going to be 20022FF. This is going to be the second page, and so on and so on. If you take a look at it, the page number is the most significant byte of the address, and the location inside the page is the least significant byte in the address of the page. So it's just the way the pages are addressed and the way the memory is referenced. It doesn't change the way that we are going to be thinking about it, but it helps. Because if you're dealing with pages, you can also see that sometimes you're going to be needing 16 bits to refer to a value. Sometimes you're going to be able to use only 8 bits. So you need to make sure that you know what you're trying to do. There is also another addressing mode that we are usually not using, and it uses the register X. And this one is a little bit complicated, because this one says this. It uses the parentheses, but the parentheses are outside of the entire equation. So what this does is it goes to the location 10 and gets the value from there. It adds the X, then it goes to that location in the memory that the entire equation equates to, and then goes there and gets the information from that part of the memory. This is rarely used, but it can be used, and it's one of those things that you are going to be learning much later, because you're going to be struggling with normal addressing and normal indexing, and then after a few hours spent trying to debug things, you're going to be understanding why you should even need a thing like this. Why are we dealing with different modes of addressing, and why are we dealing with different ways of talking to the memory? Because 6502 does not understand types. When we say types, those who are doing the programming among you, you know what the type is. So a type of the number means that a value has a different meaning to you. For example, it can be an integer if the number is a whole number, or it can be a float if a number is a fraction, or you can do double floats, you can do bytes, you can do values that are letters, for example, and so on. And 6502 does not understand this. 6502 is simply referring to bytes in the memory. It doesn't know if the byte you're storing is part of the floating point number that you're trying to reference. If you are dealing with something that can be considered, I don't know, a letter, or a part of the memory that is being referenced just to be full of pointers to different parts of the memory. So 6502 only knows that there is an address. This address contains a byte of data, and then depending on what you're trying to do, this byte of data can be either an opcode, or can be an operand, or can be just data for some different command to execute. So 6502 is referencing everything as memory, and then when we need to create a different data type, for example a matrix, or we need to create an array or something like this, we need to do it by ourselves. This is the reason for the indexing modes. For example, if you need to create an array of bytes, you simply just use the X register and just create a start of the array, and then reference different elements in the array as different indexes in the array. Different commands can be used when we are dealing with the registers and the memory. LDA, LDX, LDY are used to load the register A, X, and Y, but depending on the mode that you are using, some of the modes are not available to you. All the memory load and store instructions are going to affect the N and Z flags. So for example, if you take a value that is going to be negative from the point of view of the processor, and store it into the for example register A, the flag N is going to be raised. If you put 0 into any of the registers, the Z flag is going to be raised. The counterparts of those LDA are STA, STX, STY. These mean that you are storing the information from the register to the memory. So different direction, but the same thing. You also have some instructions that are able to transfer information from register to register. Almost all the combinations are available. So you can transfer from A to X, A to Y, X to A, Y to A, X to S, S to X, and so on. You will notice here that some of the registers are not available, and this is the reason why things can be complicated sometimes. But also there is a reason to why this is like this, and this is to avoid complexity in the hardware itself. 6502 is a simple hardware design, and creating a way of being able to transfer data between each and every one register to each and every one other register is much more complicated than it is to just wire, because you need to hardwire some of the registers together. Then we come to stack. Stack has two instructions that are able to hold the stack and use additional register to hold the context. Context being the current value of the stack. So you can transfer the stack to the register X or transfer the register X to the stack. Then we have either a push or a pull. Push being PHA, meaning get the information stored or the byte stored in the accumulator and put it to stack. This is automatically move the stack pointer one location down, or it is going to decrease the stack pointer. PHP is going to put the flag register to the stack, the entire flag register, so all the flags are going to be stored. And this is important because the processor does not understand how to call a function. There are no functions in the assembly. So if you need to do something, you need to store the current value of the flags, because the next operation that you perform is going to override them. So if you're calling a function, or if you're calling something like an interrupt, this means that you're going to be dealing with the flags, and if you need to go to interrupt routine, first you're going to usually store the flags, so you can go back to where you were before the interrupt was called. PLA and PLP are the exact opposite of the PHA and PHP. PLA means go to the top of the stack, whatever is there, put it into the accumulator A, and then move the stack pointer up. And PLP is going to do the same thing with the flags. So it's going to take the value from the stack and put it into register P. One note of caution here. The processor does not understand what is on the stack. It does not understand what is the value that you are storing there. So if you do not make, if you're not paying attention, you can simply go and move information that was not meant to be into the stack in the flags register and try to move it from the stack there, or you can pop the value of the flags directly to the accumulator because you weren't paying attention. So try to, when you're dealing with the stack, try to remember what was the first value that you put on the stack. So for example, if you wanted to store the first the A and then the flags, you would put PHA and then PHP. But once you are finished, you would then do a PLP and then PLA, because the stack is last in first out. So if the last thing that you put on the stack is the flags, you need to pop the flags first. So you're going to do it the opposite way. Same goes with the calling on the functions, but we are going to be dealing with this later. When it comes to arithmetics, there is a lot of different instructions that you can use. We were talking about ADC and SBC, so the addition and subtraction. Subtraction requires you to set the carry flag before you do the subtraction itself. So have that in mind. It's just the way the processor works. So you need to set the flag if you want to have the subtraction be correct. Increase and decrease, or inc and dec, can be used to increase and decrease the value of the memory, or in the memory allocation. You can also increase and decrease the value in the register X and Y. You can do comparing, so you can compare the operand or the value after the instruction to A, to X, or to Y, depending on the instruction that you are going to be using. And then based on this, you are going to have you're going to be able to use branching. So you're going to be able to understand based on what the comparison did. You're going to be branching either if the value was less than, more than, or equal to a certain value. So you can do the using the arithmetics and the compare function. You can do the branching, and you can do conditional branching. Logic is interesting because first, the logic functions work with the A register, and logic functions have an operand. So whatever is in the A register is one of the operands, the other is the one after the instruction. You also have shift left using the carry. You can shift the operand right using the carry, and you can rotate to right and rotate to left. So you can just take whatever bit is on the leftmost side and then put it on the right and move everything on the right, and vice versa. You can also bitwise compare, bitwise AND the value after the bit instruction and compare it, do the logical instruction and on the accumulator. And this is one of those things that are immensely important once you're doing something, because logic instructions in processing and in the assembly is something that is used when you need to speed things up. You're going to be doing a lot of XORs and a lot of ANDs and ORs when you're dealing with not only the numbers, but also the way the numbers are stored. So you're going to be using something called masking, and we are going to be dealing with this later. Now, for the branching. You can either jump unconditionally, or you can do the branching. Branching means that your application or your assembly program is not going to run linearly, but it is going to branch, or it's going to change its own execution path. Usually the programs are running just each instruction after each instruction, the way they're stored in the memory. And once you try to use the branching, you are going to be changing this. We already had an example that was using the branching. It is using the idea of being a number being 0 or not being 0, being positive or not being positive. We can more or less branch based on what the result of the last instruction was. So your branching is going to be based on the flags. BCC, BCS are there to jump if the C flag, so the carry flag, was clear or set. BNE and BNQ are going to jump if the 0 flag was clear or set. BPL and BMI are going to jump if 0 or not 0 flag was set, and this is not correct. This should be negative. This is not jump if 0, this is jump if negative. And then we have BVC, BVS, jump if V flag is clear or set. I'm going to be talking about the overflow flag later, when we are going to be dealing with the different ways that the numbers are represented in the memory. Conditional branching is always relative, so we can only jump relatively to the code that we are dealing with. It is always 8-bit and signed, so you cannot jump more than 127 locations up or down from the location that you are currently in. This can be a problem, but it is easily solved. Jump instruction, the first one, JMP, is the unconditional jump. This instruction does not take care about anything other than it being there. So whatever you put after this is going to be pushed to the program counter, and then this instruction is going to be executed later. And this is the way to just go to a particular part of the memory and just start from there. Usually what we're going to do is usually we're not going to be using jumps in such a way. We're usually doing branching, but sometimes jumps are inevitables. Also, notice that there is no way here to go back. You are jumping and you're just setting a new value, and you're just going to go to another location that's going to be probably referenced to by a label, and that's it. If you want to do a jumping and then go back somewhere, we are going to be dealing with subroutines. Subroutines are using two different instructions. One is JSR and the one is RTS. JSR means jump to subroutine, and RTS means returns from subroutine, or return to location where you jumped from. But this is going to be a topic for another episode. For now, I'm going to stop because I think that we have reached the first part of the what 6002 can do. And what I'm going to show you is just a couple of things. First thing is how 6002 actually looks like. And what I'm going to do is I'm going to show you the 602 Visual 602. This one broke on me because it took too much memory. This is so-called Visual 602. It's a site, visual602.org, and this site is using the HTML features to create the representation of the actual processor. So what you can see here is how the processor actually looks like. This is the inside of the processor, and you can see different transistors in different parts of the processors running the code that is here, and this code then makes part of the processor active, and flashing means that you are able to this part of the processor is currently has power connected to it, or has this active signal connected to it. This is a nice tool to make a connection between what you created as a program and what is actually happening inside the processor, because sometimes we don't understand what did we do when we said, for example, as I don't know, LDA something. We created a signal path inside the processor, and it told the processor to do something. Then it tries to use the opcodes and tries to understand how to create the information, how to create the data that we wanted, and put it inside the registers. 602 also has links to other things that we are going to be using later. I'm going to just mention that there is something called Easy 602 tutorial, and there is a disassembler from Masswerk, and we are going to be using those later in the next episode, because I'm going to be going through both of those. 602 Easy is one of the best learning tools when it comes to starting with the 602, and all the different examples that I used here can be run in this assembly emulator. Also, the Masswerk disassembler is a little bit more complicated, but it is much more akin to what it would look like if we had the actual processor, and the workflow in this assembler is much more like what you would do normally. So you would normally write down your code, you would compile it, then you would, or assemble it, then you would get the hexadecimal version of your code, then you would put it somewhere in the memory, and then you would tell to the processor where to start and to start running the code. But more on that in the next episode. Thank you for being with me. I hope it wasn't too complicated to follow me in this short tutorial, and I'll see you in the next episode. Thank you.